Okay, so again, we're drawing what problem was this one? It was number
19.
6.19.
7.19.
Oh, right, chapter 7, number 19. So it said like the ith bug is drawn independently of or the ith type of bug is drawn independently of the other ones, and the only requirement or the only stipulation is that like P1 is the probability. Oh, hang on, I'll just write. Okay, so I'll just say PI is the probability that bug I is drawn. Okay. And where did I go from? It was like, how many bug types were there?
There were R.
Okay, so 1 equal to or less than I equal to or less than R. So in other words, the sum of the PIs is 1. Okay. Then you said, so the first question was, how long does it, or what's the expected length of time until till bug number 1 is drawn or something, right? Was that right?
It was the expected number of bugs caught before bug 1.
Right. So if G1 is the number of bugs until bug 1, right? That's going to be distributed as, right? Isn't that just a geometric with probability P1 or something?
Yeah.
Yeah. So the expected value of G1 is just 1 over P1. Is that what you got?
I had to subtract 1.
Oh,
Um,
okay.
it's the number of insects that are caught before the
Oh,
first type 1.
okay. Right. So it's the number of bugs until, oh, okay. So maybe, yeah, this is just a geometric -1, basically. Yes.
Yeah.
You're just counting the things before it. Okay. So then, yeah, that's right. Okay. So then this, yeah, right. This is going to be 1 over P1 minus 1, basically. Yeah.
Yeah.
And I think that this was trying to push us in the right general direction for the second part. Okay. So how do you think we should define, okay, so like read to me the question again.
Part B.
Yeah.
Compute the mean number of types of insects that are caught before the first type 1 catch.
Okay, compute the mean number of, okay, so read that again.
Compute the mean number of types of insects that are caught before the first type 1 catch.
Mean number of types caught before what? Before
The first type 1 catch.
the mean number of types caught. And then your strategy, right. The mean number of types that are caught before type 1 is caught. And you had a bunch of indicator variables or something, right?
Yeah, so I define each y sub I means the ith bug was caught. before the first type.
Right. Okay, yeah. I think this is what I was thinking. So G so G2 is going to be the number of bugs until what? What do you think?
Until type 2 is caught.
Yeah, type 2. I don't like that I wrote bug. Right? This is type. Type 1. Type 2. Okay? And this is going to be geometric P2 minus 1, right? And in general, GI is just going to be the number of bugs until type I, which are all going to be geometric PI minus 1. Okay, and the way, okay, and so the way that we're going to find the mean number of types caught for type 1, so T1, this is going to be the number caught before type 1. Okay, and what we want then is just the expected value of T1, yeah?
Yeah.
But isn't it true that T1 is equal to the indicator of the following event, or the sum of indicators of the following event? It's the indicator of G2 being smaller than G1 plus the indicator of G3 being smaller than G1 plus etc. GR smaller than G1. Does that make sense?
Okay. Yeah. So do you
So if
just,
the number of bugs caught before the second bug type is smaller than the number of bugs caught before the first bug type, then I know I should count bug type number 2. Does that make sense?
yeah.
Yeah.
So do you just assume that you caught type 1 on the nth catch and then calculate the probability that you catch type I in one of the n minus 1 catches?
Well, I think okay, I think what this is going to boil down to is you're going to compute the expected value of T1. Yeah.
Yeah.
And this is simply going to be, look, all of these are going to have the same expected value. Because G2 through GR, I mean, and they all have, well, actually, no, that's not true. They're not going to have the same expected value because it depends on, right? G3 depends on a particular probability. Yeah. So
Okay.
it's going to be the sum I going from 2 to R, the expected value of the indicator of the event G2 less than G1. Okay. Which is going to be the sum I going from 2 to R. What is the expected value of an indicator variable? Isn't it just the probability of that event?
Yeah.
So it's going to be the sum of the probability, or actually this shouldn't be a 2 right here. What should this be? Sorry.
An I.
Yeah. should be the probability that GI is less than G1, and that's way easier to compute. Yeah. So let's do that. What's the probability that GI comes before G1?
So
Agree with what we've done so far?
Well, if you assume G1's caught on the nth catch, right?
The nth catch.
Or
Well, I mean, so this computation that we've done so far, do you agree?
yeah.
So we just need to figure out what's the probability that GI is smaller than G1, right? So, so how are we going to compute that?
Using the geometric, right?
Yeah, right. So right. So we need to compute the probability that GI is smaller than G1, right? And to do that, we need to go, okay, this is going to be the sum, right? And you want to say that like G1 is on the nth catch or something like that, right?
Yeah.
Okay. So by the way, before we do that, right, this is just the probability of a geo with probability pi minus 1 being smaller than a geo with probability p1 minus 1, right? Which is just the probability. Look, you can just add 1 to both sides. Less than the geo with probability p1, okay? Okay, so this is 1, okay, so hang on. So let's do it like this. So this is 1 minus, I want to get an equal to in here because it'll be slightly easier to deal with. 1 minus the probability that GOPI is equal to or greater than GO of P1, right?
Okay.
And if we have, so if X is distributed as GO of P, okay, and this thing has range of values, all the positive integers. What was the probability mass function for this thing? Do you remember?
That was, well, P times 1 minus P
Mm-hmm.
to the X minus 1. Yeah.
Yeah. Okay. And what's the probability that X is equal to or greater than some little x, which it seems like that's what we're going to need to know, right? What's the probability that X is equal to or greater than little x?
It's the sum from X to infinity
Mm-hmm.
of 1 minus P to the X minus 1 times P.
Okay, or right, or plus 1 minus P to the X times P plus, right, I'm just taking different values beyond X, right? 1 minus P to the X plus 1 times P plus etc. And we can like factor out 1 minus P to the X minus 1 times P, right?
Yeah.
And then what's left behind? 1 plus 1 minus P plus 1 minus P squared Okay. And what's that going to be? 1 minus p to the x minus 1 times p over 1 minus p, right?
Yeah.
So the p's cancel. And you end up with the probability that x is equal to or greater than x. For some reason, like the CDF, like the reverse of the CDF is almost easier to work with for the geometric, right? So the
Yeah.
probability that x is equal to or greater than x is just 1 minus p to the x minus 1. And we kind of reasoned at some point that that made sense because that just means that you had 1 minus p failure or x minus 1 failures at least. And then whatever happens after that, we don't care. Yeah.
Yeah.
All right. So back to this thing right here. How are we gonna let's at least get this set up on this whiteboard. So you're gonna go 1 minus the sum. Say, okay, so what's this? So what are we gonna do here?
I mean, just using the what we derived. That's 1 minus p sub I.
Well, except
Uh,
I need to first kind of I need to condition on the probability that, right? So right. So it's going to be the sum x going from 1 to infinity. Okay. And it's going to be the probability that the GOP1 is equal to x. Okay. So let me just say it's the probability that GOP1 is equal to x. Oops. Times the probability that GO of PI is equal to or greater than that, equal to or greater than x, given that GOPI P1 is equal to x. So it's going to be the probability that GOPI is greater than or equal to x. Does that make sense?
yeah.
Okay, so let's go to the next slide. Okay, so I want so let's just write it down. The probability that GI is greater than, or wait, was it greater than or less than? Sorry,
Uh,
less than,
yeah.
okay. Okay, less than G1 is equal to 1 minus the sum. I said x was going from 1 to infinity. The probability that GO, was it GO of P1?
Yeah. Equals x.
Yeah, times the probability that GO PI is greater than or equal to x. Okay. So it's going to be 1 minus sum x going from 1 to an infinity. This is going to be P1 times 1 minus P1 to the x minus 1 times, okay, what's the probability that GOPI is equal to or greater than x?
That would be the sum from x to infinity.
Well, but we just got a formula
Yeah.
for the
So
geometry.
that'd be 1 minus p sub I to the x minus 1.
Yeah. Yeah, we could have written it as a sum. And I think, okay, all right, so I mean you'll see what's going to happen here. So so this is 1 minus P1 times what? Okay, if you take x to be 1, you could just get 1, right? Plus, what's the next term? If I take x to be 2, It's just 1 minus P1, 1 minus PI. Yeah?
Yeah.
Plus, what's next?
1 minus P1 squared, 1 minus PI squared.
There it is again. Okay. So it's going to be 1 minus P1 over, oh man, over, oops. It's going to be 1 minus P1, 1 minus PI. Okay. Okay.
Yeah.
Yeah, let's just leave it at that. So then what's the expected value of T1?
It would be the sum of, well, from 2 to R of that.
Yeah. And I don't think that you can, I don't, think here. Yeah, I don't think we can I don't know that we're going to be able to simplify it much more than that. I mean, you could write this as R minus 1 minus this sum. I don't immediately see a way to necessarily simplify that. I mean, of course, you could factor out P1, for instance, but without knowing more about the PIs, I don't think that you can necessarily simplify more than that. But what I was saying before was, when I was messing with that sum we came up, like there was a massive amount of simplification that happened at some point. And I don't remember if it looked exactly like this in the end, but that just made me think that something simpler was going on. And so that made me to think of, okay, like there's a reason they gave you in the first part, they moved you toward a geometric. And so all we did here was we just used geometrics for all of them. And we said, well, we just need each one of those geometrics to be prior to the first geometric. Or we need to count the number of those geometrics that come prior to the first geometric. And so we just had to set up our indicator variables differently. Does that make sense?
Yeah.
At least makes sense that it would be R minus 1 minus something. Yeah.
Yeah.
Because R minus 1 would be R minus 1 would be the total.
Possible types of bugs.
Yeah. What if, is there something we could plug in to like check and make sure that, like, what if P1 was 0? Oh, yeah, this gives the correct formula. If P1 was 0, do you see that the sum would disappear
Yeah. You're just left with,
at R minus 1?
yeah.
Right?
Yeah.
And what if P1 was 1?
Well, you get You get the sum reduces to I from 2 to R of 1. So you just get R minus 1 minus R plus 2, so you get 1, right?
So hold it. So if P1 was 1, it would be 1, right? Like the summand would just be 1. Isn't that right?
Yeah.
So then, but that's R minus 1 terms.
Yeah. Okay, yeah, sorry.
Yeah, so you would get 0, which is exactly right, isn't it?
Yeah.
Okay. So, I mean, that's at least comforting that this thing is delivering the correct result in those two boundary cases. Okay. So I think you'll agree that that's a much simpler approach than than what
Yeah.
we had before. I think that the other approach was actually correct. And there was just a massive amount of simplification that happened where I was like, man, what is going on with this? I kind of stopped partway in, and that's when the geometric idea kind of occurred to me. So yeah.
I think my problem with it was I was constantly ignoring the geometric with for type 1. So,
Oh, I see. Yeah. Yeah. So I think that that was kind of the key. And the reason I brought it up in the context of order statistics is it is kind of like it is in some sense an order statistic problem because you're comparing um you're basically comparing where G1 is relative to everything else, right?
yeah.
Relative to all of the other geometrics. So there's probably another way to do this using the stuff about order statistics, but you would have to condition on which one of the order statistics G1 actually was. Like if it's in, position 1 or position 2 or position 3 or something. And you probably could come up with a formula using order statistics also. So that's also kind of what I was thinking about. But it's an interesting problem, no doubt. Sweet. Did you have other questions?
No, not at the moment. I feel
Okay.
like a lot of my time was spent on that problem.
Okay. Well, is that at least a satisfying conclusion to that?
Yes.
Okay, good. That has to be the solution. I mean, look at it. Look how nice it is. That has to be it. um, did you watch the lecture on order statistics yet?
Yes.
Did that make sense?
Um, it makes more sense in the book, yeah, because I think I understood how to use it, but I didn't really know where it was coming from, so that made a lot more sense. So,
Unfortunately, they tried to do some kind of heuristic approach using the density, and I didn't understand why they did that. So they said, "Oh, it's within epsilon of this thing," and I'm like, "Why would you do it that way?" Um, you could just approach it directly with the cumulative distribution function and invoke the binomial random variable, and that really does give everything. I also don't really appreciate their notation. Um, I mean, I understand where they're coming from, but I just don't like it whenever I have to put parentheses around like a subindex. It's annoying to me. But yeah. Yeah, those graphs were pretty cool, I thought. You can kind of
yeah,
the distribution kind of humping up from left to right.
yeah.
So that was kind of a satisfying conclusion to that. Well, anything else?
Um, no, thank you.
Yeah. All right. Thanks for coming and asking. All right.
Bye.
See ya.